Assalamualaikum and a very good day to everyone. So today we will continue our lecture in this topic, where today we will discuss about the potential difference and also the absolute potential. So this is the objectives which I have explained in a previous lecture. Yeah, so we will follow this objective for this lecture. So previously, we have learned about the work done, right? Where we know the work done can be calculated using W negative, the initial position, and the final destination, where it's gonna be the QE or the force, dot dl. Okay, so from here we can calculate the work or the total work done when we want to move a charge from one point to another. Okay, so let's say we want to move a point charge, from point B to point A. So point B is our initial point and point A is our destination. So it can be written as negative integrations of QE, right? The QE. But then we know the Q is a exact value, and we can bring it in front. And let's say we want to calculate work per unit charge. Okay, work per unit charge. So we can move the Q to the other side. Okay, so it will be work per unit charge. So therefore, the work done per unit charge, will gonna be the negative integrations, the initial destination to the final destination, E dot dl, and the unit will gonna be volt. So from here, we want to calculate, let's say we want to calculate the potential difference, potential difference between point B and point A. Okay, so the potential difference, can be calculated, since that we want to calculate from point B, where our point B is our initial point and point A is our destination. So your potential, usually is represented in a volts, so it's gonna be in a V. So your initial to your final, right? VBA is equals to work done per unit charge. Okay, so work done per unit charge is also known as a potential difference. Okay, so it is equals to the negative integrations, your initial destination to your final destination, E dot dl. And it also can be represented or can be calculated by, we know the potential at point A, okay, minus with the potential at the initial potential. Okay, potential at the initial position. So VA minus VB. So this is what we call as a absolute this is what we call as a potential difference. Okay, meaning that the potential difference between two exact point. Okay, so in this case, point B and point A. All right, so now we want to know what is absolute potential. Alright, so absolute potential is when your initial point, okay, your initial destination or your initial position, initial, okay, when your initial destination is in infinity, meaning that it is located somewhere very, very far away. Okay, your origin or your initial position is very, very far away. Alright, so your absolute potential, okay, will be, alright, infinity until point A. Alright, so let's say we want to use the same equation as potential difference. So it's gonna be W over Q, okay, work per unit charge. So it's equals to VA, your final destination, minus with your initial position. So now your initial position is infinity, right? So let's say we want to make it as integrations. So it's gonna be integrations start with infinity, it ends at position of A, E dot dl. Alright. Alright, and when you proceed this, okay, when you find your calculation, okay, when you proceed this, you will get that your for absolute potential, yeah, for absolute potential is equals to potential at your final destination, which is only potential at VA only, right? So when you further calculate this, or you can see the explanation in your reference book, okay, you will see that when your initial destination is at infinity, okay, the absolute potential is equals to the potential at your final destination only. Alright. Alright, now let's look at more details regarding on the potential difference. Okay, so now the example is regarding on the point charge. Alright, so we have let's say we have a point charge where the value of the Q, yeah, is 1 coulomb, and we want to move it from point B to point A. So the distance of the charge from point B is given as RB. Okay, the distance of the point charge from point A is given as RA. Okay, and we need to find the potential difference between point B and point A. So potential difference from point B, okay, to point A, we're going to be VBA equals to negative integrations of A, the lower limit we're going to be the initial point, the upper limit we're going to be the destination point, okay, B to A and E dot dl. Okay, so E, the value of E, right, we have obtained from the Coulomb's law, right? From Coulomb's law, the E for a point charge is given as Q over 4 pi epsilon naught R squared in R direction. Okay, since that it is in a R direction, we know the equation that we will involve here is in dot product, right? So your DL also should be in R direction, because same direction for a dot product will give us value. Okay, so since your E in R direction, your DL also should be in R direction. Okay, so if you further to calculate, okay, so if we further to calculate, we are able to get, yeah, VBA is equals to, we want to use this equation, yeah, negative integrations where it start at RB, it ends at RA, okay, and the value of what E fit we're going to be Q 4 pi epsilon naught R squared in R direction dot dr in R direction. Okay, so we can bring all the constant in front. Okay, let's bring all the constant in front. Q over 4 pi epsilon naught. Okay, so it we're gonna leave behind integrations of from RB to RA 1 over R squared. This is A, yeah? Okay, dr. Okay, so if we further to proceed the mathematical operation, you will get, okay, your value will gonna be Q over, we want to let's say we want to remove this negative, you just have to shift, yeah, the positions of this limit, yeah. You can remove this negative by shift the position of upper limit and lower limit, right? So that is mathematics lah. Q over 4 pi epsilon naught it will be 1 over RA minus 1 over RB, and the unit will gonna be in volts. Okay, the unit will gonna be in volts. So you can see the potential difference, okay, from point B to point A. Okay, from point B to point A, it will be 1 over RA, which is the end position, okay, minus with the initial position. Alright, so now let's say we want to have the absolute potential. Okay, how about the absolute potential? Okay, so for absolute potential, we know the destination or the initial point is at infinity. So now let's say B is our initial point, yeah, and B is located somewhere around infinity lah. Okay, so the destinations of B from the point charge is located at infinity. Okay, so from the BA just now, right? From the potential difference that we have calculated just now, we have obtained the Q, the value, yeah, of potential difference is equals to Q over 4 pi epsilon naught 1 over RA minus 1 over RB, right? So now our RB is infinity. So when it becomes infinity, what will happen? This will become 0. Yeah, totally this will become 0. So therefore, when your initial is at infinity, so it will be Q over 4 pi epsilon naught 1 over RA, right? So which is, this is equals to potential at VA. Alright? So this is the equation. Alright, and yeah, you will get potential exactly at that particular destination point. So now let's say we want to know, or we want to calculate the absolute potential for multiple point charge. Okay, right, so we have a multiple point charge here, Q1, Q2, Q3 and Q4 at one position. I mean one interested position lah, yeah. So what is the total absolute potential, or sometimes they just mention it as potential, okay, at A. So A is our point of interest, or the destination, yeah, point of interest. So it will be, okay, the V at A, which is our point of interest, will be the Q1 over 4 pi epsilon naught R1, which is R1 will gonna be the distance, yeah, between the first charge to the point of interest, plus Q2, okay, Q2 over 4 pi epsilon naught R2, where R2 will gonna be the distance between the charge and the point of interest, and so on. Okay, it's gonna be the summation of all the point, all the point charge, right? Okay, let's look at the example number 3 that has been provided to you. Okay, so it's given a total charge, the value of Q is given as 60 microcoulomb, is split into two equal charges located at 180 intervals around a circular loop of radius 4 meter, and we need to find the potential at the center of the loop. Okay, alright, so let's draw or illustrate the diagram for this example. So we want to find the potential at the center of the loop. We have a loop where this loop, the radius is given as 4 meter. Yeah, the radius is given as 4 meter radius. So this is going to be the center. So we need to find the potential at this part. The potential. Alright, the radius is given as 4 meter radius. Okay, 4 meter radius. And there are charge. Okay, one charge is located separate. It's split into two and located at 180 intervals. So this will gonna be from here to here, yeah, 180 intervals. So one is located at here, 30 microcoulomb. Okay, and another one is 30 microcoulomb as well. Is at another at interval. Okay, remember, yeah, this is a total charge of both of these two charges. Okay, so 30 micro plus 30 micro, so it can be 60 microcoulomb. Okay, so we need to find the V naught at the center of the loop. So therefore the potential will gonna be V at the center, okay, is equals to V for the first charge plus V for the second charge. So let's give the first charge, which one as the first charge? So this one as the first charge, and this is as the second charge. Okay, so the equation is given to us as just now, Q over 4 pi, Q over 4 pi epsilon naught R, right? So it's gonna be Q, we're gonna be 30 micro, 4 pi epsilon naught R. So R is given as the distance from the point charge to the point of interest. So the radius is given as 4 meters, so it's gonna be 4 lah. Okay, plus another one, we're gonna be 30 micro as well, 4 pi epsilon naught. So the distance is given as 4 as well. So you will get your total will gonna be 30 micro over 8 pi epsilon naught V. Okay, so this is your answer, right? So let's proceed to another example, which is example number 4. There are 3 point charges. Q1 is equals to 1 millicoulomb. Q2 is given as negative 2 millicoulomb, and Q3 is given as 3 millicoulomb. Are respectively located at 004, negative 251, and 3, negative 46. And we need to find the potential of Vp at P is equals to negative 1, 1, and 2. Okay, so that is the first questions. Okay, we need to find the potential at P given as negative 1, 1, and 2. And the second question, we need to calculate the potential difference. So for question number 2, it is a potential difference because we have another point, which is point Q, yeah, is given at 1, 2, and 3. So the first question, since that we only have one interested ataupun one point of destination, so it will gonna be the absolute potential. Absolute potential here, absolute potential. So the second one, since that we have two positions or two destination, we have the initial position and the another destination, so it's gonna be the potential difference. And if you look at the questions also, they clearly mention the potential difference. All right, so that is how you want to differentiate, yeah, between the absolute potential and potential difference. Okay, so now let's proceed with question to solve the A first, yeah. There are 3 point charges. So we have 3 point charges. One is located at Q1. Q1 is given at 1 millicoulomb. Q2 is given at where the position is given as 0, 0, 4. Another Q is given at Q2 where the charge is negative 2 milli, negative 2 millicoulomb, and the position is given at negative 2, 5, Okay, and another point is Q3 at 3 negative 4 6 yeah, 3 oh 8 yeah, 3 negative 4 and 6, where the charge is given as 3 milli. Okay, and we need to find the potential at point P, where point P is given as negative 1, 1 and 2. Okay, so now we know the equation for absolute potential is for point charge is given as V is equals to Q over 4 pi epsilon naught R okay, Q over 4 pi epsilon naught R. So we need to know the R, the distance Q1 to P. So how to know the distance from Q1 to P? So it will be negative 1 square root of negative 1 minus 0 squared plus 1 minus 0, okay, 1 minus 0 squared, square root, yeah, plus another one is 2 minus 4, yeah, squared, and you will get it is a square root of 18, square root of 18. So you need to proceed the distance Q2 to R. So you will get if I'm not mistaken, you will get sekejap ni. Oh sorry, this one you will get not 18. You will get negative 1 minus 0, 1 minus 0, and 2 minus 2 minus what? 2 minus 4. So this one you will get square root of 6, yeah? Okay, so you proceed, you will get for others, you will get this one is gonna be negative 2, right? Square root of 18, and this one you will get square root of 29, if I'm not mistaken. Please check as well the calculation. Alright, so once you know all the R, so you can just substitute inside this equation, okay, also with the respective value of Q. So your VP is equals to negative 2 over 4 pi epsilon naught square root of 6, sorry, negative 2 is square root of 18, square root of 18. Oh, mashallah, what is that? Okay, I wrongly pick up square root of 18, and then plus with 1 over 4 pi epsilon naught square root of 6 plus 3 over 4 pi epsilon naught square root of 29, right? So you add all together, you will get your answer in millivolt. Okay, so that is the value of potential at point P. Okay, so now to proceed question number B. Okay, to proceed question number B, you need to find the value or VQ first. Okay, you need to find the value at VQ first, then only, okay, once you got the answer in millivolts, then only you can proceed with the potential difference. So the potential difference VPQ is equals to what? V PQ, yeah. So VQ minus with VP that you have calculated earlier. So I leave it to you for this question for you to solve, alright? Okay, so now let's look potential for a charge system, whereby just now we have discussed in terms of point charge only. So how about for others, others charges, yeah? Others continuous system of charges, yeah, right? So we know we have others, yeah, line charge, we have surface charge and volume charge. So before that, you have to bear in mind the potential here means that your initial point, okay, I try to write the initial position, okay, the initial is at infinity, all right? So to measure the for the line charge, so your VA will gonna be the integrations of line, okay, your Q, okay, so just now your VA for initial absolute potential, or your initial position is at infinity, the equation for point charge will gonna be Q over 4 pi epsilon naught R, right? So for other charges, what you have to do, you just need to replace the Q with other charges lah. For example, for line charge, you just have to replace rho L dl. For surface charge, you're gonna be rho S ds, and for volume charge, it's gonna be rho V dV. And to measure the total, so you don't forget to put the integrations. Okay. Now let's look the example for other charges, other form of charges. So example number 5. The question asks about we need to obtain the expression for the absolute potential. So absolute potential, yeah. So your initial will gonna be at infinity, yeah, along the z-axis of a ring of uniform rho L. So it's given to us, it is a rho L, whose radius is given as R0, okay, and the ring is located at z is equals to 0. So it is located at z is equals to 0, meaning that it is lies on xy plane. So given the electric field at any point on z-axis is as such, alright. So let's illustrate the structure first. Okay, so actually there are two methods that we can use to solve this question, right? So let's use the first method. The first method, we want to use the equations that I just showed you previously, which is V equals to integrations of rho L dl over 4 pi epsilon naught R, right? Okay, so if we can illustrate the structure will kind of looks like, so this is our xy axis, xy and z axis. So there is a line, a ring of uniform, yeah. So the uniform ring is lies on xy plane. The radius is given as R0, okay, R0, and it has a line charge of rho L, okay, and we need to find the absolute potential along z-axis. So meaning that the absolute potential somewhere around z-axis, let's say it is located at up here, and the equation here is given as 0, 0, z. We don't know, yeah, we don't know what are the exact location, but we know it is along z-axis. Alright. So first of all, we want to use this equation, okay. So rho L is rho L. What is our dl? Okay, so rho L, it doesn't have any problem with rho L. There are two things that we don't know in this equation. We don't know the dl, we don't know the r. So now let's identify the dl first. So the dl for this structure, okay, so the dl will gonna be, right, so the dl for this one, yeah, So this is the appropriate orthogonal coordinate system that is to this diagram we're gonna be the cylinder, right? So it can be in r direction, phi direction, or z direction. Okay, if you look here, if you take any sample, as long as it is located along this line, okay, the r will gonna be constant, the z will gonna be constant, yeah, the sample, yeah, r will gonna be constant, which is r naught. The z also will gonna be constant because z is equals to 0. So the one that will be changed is the locations of phi. So your dl will gonna be on phi direction, so therefore it will be r d phi. Okay, so your dl will gonna be r d phi. And how about your r? So your r, we know the r is the distance of the charge to the point of interest. So from the charge to the point of interest, so this r. Okay, so your r will be equals to square root of r naught squared plus z squared, right? This to this, right? So you will get this length, right? So r squared plus z squared and square root of it. Okay, so we have all this information. You just have to substitute inside this equation. So your v will then become rho l. Your dl will gonna be r d phi over 4 pi epsilon naught. Your r is equals to r naught squared plus z squared square root of it, right? Okay, so if we proceed, okay, the integrations were going to be on d phi. So you will get the answer we're going to be integrations of d phi we're going to be 4 pi. We bring all the constant in front. 4 pi. Your r here, the r here will be the radius of the ring, right? So it's going to be r naught, yeah? R naught 4 pi epsilon naught r naught squared plus z squared half of it. Okay, integrations of d phi. So the limit we're going to be from 0 to 2 pi. So your final answer will going to be your final answer will going to be rho l r naught over 2 pi, pi will cancel, 2 epsilon naught r naught squared plus z squared half of it, yeah. Don't forget the unit in volt, right? So this will gonna be the answer by using the first method. Okay, there is another method that we can use, okay, to solve this question. Okay, another method that we want to use this e, the e that is given to us. So v is equals to negative the since that it is absolute potential, so therefore your initial will gonna be at infinity, and the final will be located at z, yeah? The destination is at z point, and then your e is given as rho l r naught z over 2 epsilon naught r naught squared plus z squared 3 over 2. It is in r direction, in z direction, it is in z direction. So your dl, since that it is in a dot product, your dl also should be in z direction, right? dz on z direction, okay, because it is a dot product. Okay, so your dl should be in z direction as well. So if you further this equation, okay, we can bring all the constant in front. It's gonna be negative rho L R naught over 2 epsilon naught. Okay, bring in front, so negative, we bring in front the limit z become z over r naught squared plus z squared 3 over 2 dz. Okay, 3 over 2 dz. And if you still remember the mathematical formula for this one, so later on you will get your answer. It will be negative rho L R naught over 2 epsilon naught, and become negative 1 over R naught squared plus z squared 3 over 2, where the limit is from infinity until z. So if we substitute inside here, inside the z here, okay, you will get your final answer to be, okay, your final answer to be, I write it here, rho L R naught over 2 epsilon naught R naught squared plus z squared 1 over 2, sorry, 1 over 2 volts. Okay, so you can see if you are using the first method or the second method, you will get the same answer. So the second method, actually we are using E dot dl, E dot dl, integrations negative, right? Alright, so now let's look the last example inside your slide. Okay, example number 6. We need to obtain the absolute potential inside and outside. They ask about absolute potential, so your initial will gonna be infinity. Inside and outside a tin shell. It is in a tin shell, centered at the origin. Okay, centered at the origin of uniform rho s and of radius r naught, and we need to obtain the potential at r when is equals to r naught divided by 2. Second condition, r is equals to r naught, and the third condition, r equals to 2r naught. Okay, first of all, we need to illustrate the structure. So the structure, we have a very thin shell. It is centered at the origin. Okay, so it is actually a sphere shape. It is centered at the origin, and then what else? The other information is given to us. The radius is given as r naught. So the radius is given as r naught. And then what else? It has a surface, uniform surface charge. So surface is given to us. If I put it inside, it will look like a volume, right? But then it's only a surface, so only exists on the surface, rho s. Okay, so first of all, in previous example, just now, in example number 5, we have two methods of solution. First, we are using v equals to integrations of rho s ds over 4 pi epsilon naught r, right? And another method that we can use also is v is equals to negative integrations of e dot dl. Okay, so there are actually two methods in this case, that we can use. So let's look in this question. Okay, in this question, we need to find the absolute potential inside and outside. So meaning that your R is can be inside, which is located somewhere around here, inside and outside this spherical shape. Okay, this spherical shape. And based on our previous based from our previous, okay, first of all, we can find the E. If you still remember, to find the E field, to find the E field for this structure, okay, we can use a Gauss law. If you still remember, right? Why we can use a Gauss law? Because it fulfills two conditions. First of all, it has a uniform charge distribution. Okay, uniform charge distribution. And the second thing, it is in a spherical shape, thin shell. So of course it is a spherical shape, so therefore to find the E field we can find using the Gauss law. So when the E field can be obtained using the Gauss law, okay, the only method or the only formula that we can use to find the potential or the absolute potential is only by using this formula only. Okay, remember, if the E field can only be obtained by using the Gauss law, okay, which is it, in this case it is a uniform charge distribution and also spherical in shape, you can only use V equals to negative integrations E dot dl in order to find the absolute potential. You cannot use rho s ds over 4 pi epsilon naught r. Okay, remember that. Okay, so now the E field, when r is lesser than r naught, okay, r is lesser than r naught, so there will gonna be no charge inside this sphere. There will be no charge inside this sphere, so therefore your D is equals to 0 and your E also will equals to 0. So this is our first condition of E field when your R is lesser than R naught. However, when your R is larger than R naught, will there be charge exist? Yes, right? Because the surface charge is already included. So your D is equals to rho s R naught over R naught squared, R naught squared over R squared, where your R is larger than R naught, on R direction. And your E will then become, you just have to divide with epsilon naught, right? R naught squared over epsilon naught R squared in R direction. Okay, so we will use both of this E to calculate the potential, okay, inside and outside. So the first condition, your R is R naught over 2, meaning that the distance of your R is inside the sphere. Okay, so the VA for first for first question, the VA when your R is equals to R naught over 2, okay, is equals to negative integrations of, so absolute potential, it start from infinity, right? So your A is equals to R naught over 2, okay, over 2. Your E dot dl, okay, right, E dot dl. So what is our E? So now we need to decide our E. Okay, if you still remember, absolute, the limit is come from infinity. So infinity meaning that it is coming somewhere around outside from the spherical. Okay, and it reach to this position. Okay, where from infinity to this position, where this position is r naught over 2, right? So therefore your E will then become, okay, so this is things that you need to pay attention, yeah. So your E will become from the infinity, okay, from the infinity, and before it reach, okay, before it reach to, okay, before it reach to r naught over 2, it will reach this distance, right? It will reach the surface of this sphere. Okay, I repeat, yeah. Before it reach from the infinity, okay, the origin now is located at infinity, and to reach to r naught over 2, which is the destination, first of all, it must arrive at the surface of this sphere. Okay, it will arrive at the surface of this sphere. So therefore, the limit will become, from the infinity, it will reach the surface of the sphere. So therefore, it will reach the r naught first. Okay, r naught, which is the surface of the sphere. So at the surface of the sphere, what is the value of E field? The E field is given as such, right? The E field, okay, at r is larger than r naught. Okay, at the surface of the sphere, there is E field inside that. So let's give this E field as E field 2, and this one is E field 1. So E field 2 dot dl plus, okay, so now from, to arrive, okay, to arrive from the surface now, to arrive to the final destination, so it will be, the limit will gonna be from r naught to r naught over 2. Okay, so now the limit will become the limit will become from r naught to r naught over 2. Okay, so it will be, so the environment now, it is inside the sphere, so it will be, the E field will become E1, yeah, this E field, all right, E1 dot dl. So we close the bracket. Okay, so negative. So for this part, we know the E1, it becomes 0. There's no electric field inside that particular sphere, so definitely behind here it will become 0. Only the E2 here has a value. So now let's try to solve that by substituting the E2 that we have obtained just now. This is the value of E2. What is your DL then? So our E2 in R direction, so your DL should be also in R directions, right? So your DL will be dr in R direction. Okay, so therefore it's gonna be negative infinity, negative, the limit will gonna be from infinity until r naught. Your E2 will gonna be rho s r naught squared over epsilon naught r squared in R direction dot dr in R direction. Okay, and if you solve this, you will get your answer to be rho s r naught over epsilon naught volt. Okay, alright. So the trickiest part, I think, for this question is how for you to decide. Okay, how for you to decide the limit for this area. Okay, from the infinity until r naught over 2, I think no problem. But then how to separate the E field? Okay, which is from the infinity, it will arrive at the surface of this sphere. So it will be, the limit will gonna be infinity until r naught. Okay, which is the environment here. If you look, the E field is R larger than R naught. Yeah, R is larger than R naught. So therefore, the E field will be E2. Okay, the E field will gonna be E2. Whereas after that, from R naught 2 R naught over 2. So the environment is inside the spherical. So it will be R lesser than R naught. So it will gonna be, instead of E2, it is E1. Okay, so it is E1, right? So be careful for this. So now let's look on the second question. Okay, wait. On the second question, where your R now is equals to R naught. Okay, so R now is equals to R naught, which is, this is our diagram. Okay, this is the radius. So our R now is located at R naught. Yeah, so meaning that it is actually at this, on the surface of this sphere. Okay, so the VA is equals to negative infinity until R naught E dot dl. Okay, so if we understand, the origin will start from somewhere around here, yeah, somewhere around infinity here, and it will reach until this position. Okay, so the environment of E field that involved inside here is R larger than R naught, yeah, which is here, yeah, R larger than R naught. So the E field that will be involved is E2, yeah, E2. So let's proceed the calculation. So the limit is R naught. So the E field that involved is E2. Okay, the dl same as before, since your E in R direction, your dl also should be in R direction. So when you proceed, you will get your answer same as before, which is rho s R naught epsilon naught volts. Okay, right. So now let's look question number 3. This is question number 2, yeah. Question number 3. So question number 3, they ask when your R is located to R naught. Okay, meaning that, so this is your structure. It has R naught radius. So now your area is somewhere around here, yeah, 2 R naught. This is your area, and this is your origin. Sorry, I should use purple color. So this is your origin somewhere around here, and it will arrive up until here, yeah. So the environments of your E field is still the same, yeah. R is larger than R naught, so we're gonna use the E2 field. So we just proceed here. VA is equals to negative infinity, and this distance, the R is 2 R naught, right? 2 R naught, yeah. So the limit is until 2 R naught. So your E that involved is E2 dot dl. So if you proceed your calculation, you will get your answer to be rho s R naught over 2 epsilon naught volt. Okay, alright guys. Okay, I think that's all. So for the next lecture, please prepare, have early reading on potential gradient. Okay, early on potential gradient, and also the energy density in electrostatic field. Thank you so much. I'm so sorry because the length of this video is quite lengthy, compared to the previous one. Thank you guys.